Okay, I think we left off at integer literal, so I'll get started. Okay. Nearly as easy to parse as identifier are integer literals, which looks like this. Yes, that's it. Integer literals are expression. The value they produce is the integer itself. Again, imagine in which places integer literals can occur to understand why they are expressions. We can use any other expression instead of integer literals here, and it will still be valid. Identifier, call expressions, group expression, function literal, and so on. All the expression types are interchangeable, and integer literals are one of them. The test case for integer literal looks really similar to the one for identifiers. Parser test. We're writing the test case first. Integer literal expression. Enough statements. Got the program statements. Okay. Program statements. Casting statement. It's not AST, not expression statement. Yeah, it's just we are just doing a comparison. We need to define token literal AST. AXT expression interface just as identifier does. So integer literal is just integer. This is the field that's going to contain the actual value of the integer literal represents in the source code. When we build an AST integer literal, we have to convert the string in AST integer literal token literal, which is something like 5 to an int 64. Okay, so we need to parse it. Alright. Okay. Parse integer literal AST expression. AST integer literal token peeker token value here parse int peeker token literal 064. Parse integer literal string. Okay, so parse integer literal. So p token. Create an integer literal AST, and then turn that into an int. If there's an error, turn it to the p.error. And then we put the lit.value once the converted value. Okay. Parse identifier. The method is strikingly simple. The only thing that's really different is a call to a string. Parse blah blah blah. We have a nil. Run the test real quick. Go test. Parse expression can't find prefix parse. Oh, we need to parse integer literal. We need to register it. What? Int. Parse integer. Okay. There are two prefix operators in the Monkey programming language, bang and a minus sign. The usage is pretty much the same, what you would expect from other languages. The structure of their usage is the following. Prefix operator expression. Yes, that's right. Any expression can follow a prefix operator as operand. These are valid. Not greater than 0. 5 plus minus add 5. Parsing prefix expression. Huh, interesting. Okay. So we're just gonna create another parser. So we have so far parse identifier and parse integer literal. Now we're parsing prefix expression. Test parsing. prefix expression T testing T prefix test struct input string operator string integer 64. Okay. Bang. So this is the expect, right? Range prefix test lexer of new tt dot input new l program p parse program check parser tp if create that PSC. T not fatal. F statement is not AST prefix. Expression got T expression if operator fatal F. Okay. This test function again has a lot of lines for two reasons: manually creating error messages for T, error F takes up some space, and we're using the table-driven testing approach. The reason for this approach is that it saves us a lot of test code. Yes, it's only 2 test cases, but duplicating complete test. So it's called table-driven test approach. Kind of sound like Lua for some reason. Yes, it's only 2 tests, but duplicating the complete test setup for each case would mean a lot of more lines. And since the logic behind, wait, doesn't Go have like something where we can loop over the test cases? Both test cases thing blah 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 differ only in the expected operators and integer values, which we define here in prefix test. In the test function, we iterate through our slice of test inputs and make assertion about their produced AST based on the values defined in the prefix test slice of struct. As you can see at the end, we use a new helper function called test integer literal to test that the right value of AST prefix expression is the correct integer literal. We introduced this helper function here, so the focus of this test case is on AST prefix expression and its field, and we will soon enough need it again. It looks like this. Just put it. Let's just put it here first. Test integer literal t testing. Here's the expression. Wow, value. It's not gonna fall. I just hope that I don't write some of this TT line value. Right? What is this? Go. Alright, type, prefix, expression. So it's probably gonna do the same thing. We just bring the type and then create a parse function for it. The prefix. Okay, so prefix token is the prefix token. Okay, operator string. Right, expression. This one is a bit more complicated, it seems like. Literal string return PE token dot literal. prefix. I'm probably gonna end this after this. P no prefix parse p dot var token dot type turn nil left is p prefix return left parse expression. Oh, that's a duplicate method. Okay. That's parser. Alright. I think I'm gonna end it here and we can get back to it. Oh, okay. Let me actually write this code. Because it seems like once you write the code, it can pass. So, okay, register it. Ah, I see. You just register a prefix.